Good afternoon. Thank you. The second part of the day after the lunch is the toughest of all. So it is not easy for the technical presentations to hold the sleep together. So we have interesting presentations from IIT Mandi and Honeywell and also from Boeing. So would like to introduce chair of the session. We have Mr. Gaurav Dubey. So Gaurav Dubey is working as principal application engineer at MathWorks, and his expertise is in model-based design, which is known as MBSE, and aerospace-related MBSE applications. So welcome, Mr. Dubey. He is the chair of the session. Over to you. Thank you.
Thank you, Shripati. As Shripati mentioned, after lunch sessions are difficult, but I'm pretty sure the three technical papers what we have are quite interesting and will keep you awake throughout the session. You have attended the multiple tracks already, so you know the drill. We will have 15 minutes for each presentation to complete, followed by 5 minutes of Q&A, right? So we will start with first session for this track. Just give me a moment. Sorry, some problem with my device. Right. So we will start with the first session, which is on the vibration frequency of cantilever beam using Harris corner detection method. And I would like to invite Mr. Lokendra Singh from IIT Mandi to talk about that. Lokendra? Okay.
Hello everyone. Good afternoon all. So myself Loken, and I am presenting here from IIT Mandi for my research study of the vibration frequency of cantilever beam using Harris corner detection method, which is a computer vision method. And so as we know, there are the various vibration analysis method like contact type and various like accelerometer, and like there are various type of accelerometers are there like ADXL 335 and various MSME accelerometers are there in market available. So what I am presenting here a non-contact type method. Non-contact type which will be low cost, which will be at low cost available in the market. What I am saying like a computer vision method where we will use a camera to detect the vibration frequency of a object of a component. So the laser vibrometer is already available in the market where we used to scan the component and we used to get the based upon the ray difference we used to get the vibrations frequency of an object. So here what I am talking about the cantilever beam. What is a cantilever beam? It is like a very simple object, a basic object where a mechanical student used to study about. It's like it's a kind of continuous object, and where like it is like all the frequencies in like more, I can say the infinite frequencies are present in this object. So I have made the study on this object. So like this analysis also, like I have seen that there are various non-contact analysis are there. If you will see in the picture A, there is a cable bridge experiment is there. So this experiment was conducted in China. So in this experiment, what they have done, the accelerometer and the region of interest they have captured, and they have made the analysis of the vibrations. So this was the CNN LSTM based network was there. Like they have got the vibrations of I can say the bridge, from the cable of the bridge. They have got the results, and based upon the from the cameras only they have got, I can say, a camera and a simple neural network they have used, and to get the vibrations, the frequencies of the various frequency modes of the bridge. So what I am presenting in my workflow, what I want, like if we can get the vibrations from this, like without using the microphone, why we can't use the, like what people are speaking around the corner. Like what I can say suppose there is like no microphone is there, only we are having the video available. If some membrane we are capturing and the vibrations in the membranes can get us idea of the what people are talking around without using any microphone in the area. So what we will use, we will use a video, like we will, what is the flow, the proposed workflow, what it says, from the video we will take the frames, then from the frames we will detect a object is moving throughout the frames. Throughout the frames, suppose we have collected around 5,000 frames, 4,000 frames from a video, and we are getting the where was the object throughout the frame. In every frame, at where was an object, and what was that the frequency was saying, like whatever the, like we are getting from then object movement, we will get the, like we will read that object, the where is the object in the throughout the frames. So what I have used the Harris corner detection technique. This is a very basic computer vision technique I have used. So simple, what is the input will be a video, and then we will extract the frame from the video. Then we will recognize the feature. A feature we will recognize, it can be a corner, it can be an edge. From that we will get a graph. It can be a displacement graph, it can be a velocity graph of then object throughout the video. So then we will perform the FFT of that object to get the various modes of the frequency of the object. Then we can get the frequency as an output. Simply, here we are not using any costly laser vibrometer or any eddy current sensors we are not using. So simply this is the experiment. I can show you here. Like there is a simple cantilever beam is there, and the frames are divided in this. So what is the natural frequency of cantilever beam? Is there 8.777? It's from the computer vision technique I have got, and I have made the comparison of this. This is the cantilever beam which is fixed at one end and free at the another end. The movement of the free end has been captured throughout the video, and where was the video moved? You can see 1, 2, 3, 4 points. These are the captured points. Where was the video? Where was the object throughout the frames? Some of the frames I have shown here, and this is the frequency FFT performed on that data. Simply here what I did, the simply tape with I have the like data mapping. What I have did here in pixel mapping, like the distance, what we want the distance as a output. So displacement throughout the frames. So displacement throughout the frames with respect to time, I have converted the pixel into the displacements. Then from those from that FFT has been performed on the data. So I will show you here like 10.6 mm. There is simple tape available in the market. That simple tape was pasted, and the corners was like tape which was 10.6 mm, and then tape with in pixel units like 43.669 pixel unit. Then it was converted into MMs. Then I got the displacement and time data. Then the accelerometer. What I got from the accelerometer, like the frequency was like what we used to. This is our conventional method we used to get the frequency of an object. So this is the frequency observed using the accelerometer was 8.918, which is very close to the 8.77. So I will say like our experiment says like using computer vision method we can get the vibrational frequency of an object also. So and it is like 98.4% accuracy of this method. What I observed from this, that's first natural frequency using the proposed technique, computer vision technique, 8.77, 8.918 using the accelerometer. And what I will say, what we got, if we are using a high speed, what I got these results using only a mobile camera, a simple Galaxy mobile camera, Samsung mobile. So what I got from that, the higher modes of vibration also can be observed. That, like as I told, that there are the infinite frequencies available in a continuous object. So higher modes of vibration can be observed using the high speed camera. If we are using high speed camera, and we can get in a second we can get the more than like 2000 frames. There are cameras like that, 20,000 frames also can be extracted from a video in a second. So what I get from as we are capturing the video from using the mobile camera, there are the various noises are there, and various problems like intensity, light intensity, and like other various problems are there if we are using. But in using high speed camera, the movement, if we are using a DC light, there will not be any fluctuation through the object in the video on as a ROI is the ROI means region of interest, where we are focusing the camera, where we want to get the frequency of the at the ROI. So what is the another insight what I get, like comprehensive data can be like there are the like as I got the 5,000 frame in a second. If I am reducing the frames, suppose there are 5,000 frames, if I am taking the, I am not reducing the time will be same. So if I am reducing the number of frames if I am taking the every 10th or 20th frame, the number of data can be reduced, and we can get the frequency in a 2 to 3 seconds, we can get the frequency of an object, and moving object, we can get the frequency. And it saves the power, and the efficiency means it can interpret quickly. Sorry. And lastly, I would like to acknowledge my guide, Dr. Arpan Gupta, and the MHRD fellowship for my PhD and my AVL lab at IIT Mandi. Thank you. I'm open for questions.
Thank you, Mr. Lokendra. We are open for the question. Does anyone have any question? Okay, if there is no question, we'll move forward. As Lokendra has to catch a flight, he has to leave now. We would like to hand him over the certificate and appreciate the presentation he did on such a nice concept.
Thank you all.
With this, we'll move to the next talk for the track today. Thank you. We'll move to the next talk for the track today. Okay, might be my phone. So the talk for the next talk is the effect of the varying diffuser vane height on CC3 NASA 4:1 centrifugal state performance. This paper was written by Mr. Sailesh Kumar, Hasham Chogule, Kezar Abdullah, and Sharman Goswami from Honeywell Technology Solution Lab. I would like to invite Mr. Sailesh Kumar to talk about that. Sailesh?
Hi, good afternoon all. So I am Sailesh Kumar from Honeywell. On behalf of our other colleagues, I am going to present this paper. So come to the outline. Outline of this paper is about the objective. I will introduce some objective about what we have what is the aim of this project, this paper. Then introduction, then some geometry calculation, then our CFD numerical modeling, and the result and discussion, and then after some conclusion. So move forward, there is the objective. So objective of this study is, I can say in some points, like as first point is, we need to validate our CFD prediction or CFD modeling with respect to the available test data, which is available in open source for NASA CC3 impeller diffuser centrifugal stage. Then second aim, once we will get the prediction which validated with our test data, then after we have performed some, we can say, some geometry changes, which known as the LSDV, means low solidity diffuser vane, basically by changing the vane height, diffuser vane height 50%, 75%, and the 100% obviously, for baseline case. Then after we have performed some study by providing the gap at between the end wall and the hub gap and the vanes, like as at the shroud, if there is a shroud gap, then between the shroud and the hub, and if there is a hub gap, then between the hub and the vane. So these 4 aim we have studied here. So you can see the introduction part. I am providing some introduction about the LSDV. What is the LSDV? Low solidity diffusion vane. Whenever there is a change in a geometry, or when there is a change in the vane, number of vane, it's known as a low solidity diffuser vane. Basically, low solidity diffuser vane is having a performance prediction in between the vaneless as well as the vaned diffuser. Like as you can see the table, that if there is a vaneless, then there is a high operating range but the lower performance compared to the vaned. And if there is a vaned diffuser, there is a high performance but the low operating range. Low operating range can be considered from the choke to stall, means a high flow to the lower flow. So come to the geometry description. Here I can say that we have used NASA CC3 compressor, which is available in literature and tested in the small engine component test facility at NASA Glenn Research Center, has been considered for this CFD study. So we have studied, first is the baseline case, which you can see the right side, that impeller rotating component along with the diffuser, and then forward by the vaneless annular passes. The geometry you can see in the graph, how we have changed. We have developed our own mathematical modeling, basically geometrical based formulation, which can be provided easily in a automation tool, basically, which can provide us varying geometry with by providing some parameter of how much we want to change, whether at the pressure side we want to change, whether at the suction side we want to change, and the radius. So you can see the leading edge, trailing edge, vase-shaped, especially I will tell you that this is the vase-shaped diffuser vane, not the airfoil vase. So vase-shaped diffuser vane we have used in this study. You can see the most right side corner, there is a how we have changed the diffuser vane height. That baseline is 100%, then 75%, then the 50%. That meridional view you can see easily. So come to our numerical modeling. Here we have used TurboGrid meshing tool, that is version 19.1 and from ANSYS, and here you can see the trailing edge we have used as a cutoff, and elliptical leading edge we have used for the other component, means impeller and the diffuser. The view of the mesh, you can see this is a fully hexahedral case, and the first cell height, like as our CFD standard, we have used our Y plus values is also as per our CFD standard, like as for different end wall, like as impeller, for blade, hub, shroud we have tabulated, and the how many number of component nodes we have used basically for this CFD study. So you can easily see the 2.5 million for the impeller and the 4 million for the diffuser. It's a 2 million for the diffuser vane. But when there is an annular passage outside of the diffuser, which is full passage up to the, we can say, combustion chamber, we have another 2 million of the mesh, that is the 4 million. So right now it is a 4 million. And the impeller tip clearance, methodology, we have used non-conformal mesh tip. And the out block we have enabled in the diffuser passage to catch the flow in the bend annular section. So I think I have missed something. So I think, yeah, here is the operating range. You can see that design inlet pressure, it's already available in the open sources. So we have used this sea level condition for our prediction, that is inlet pressure, inlet temperature, rotational speed. For the rotating component, impeller tip clearance, we have not used a nominal tip clearance, which is constant from hub to leading edge to the trailing edge. We have used a variable tip clearance, which is leading edge is a difference, then at the mid span there is a different, and the trailing edge side. So number of passes for each component is already available here, and the diffuser hub gap and shroud gap we have introduced as a 0.03, which was not available. So for this hub gap and shroud gap study, we have use this gap. So now come to the CFX modeling. We have used ANSYS CFX 19.1 to model, to prepare our CFD model. So you can see the for baseline for diffuser with 75% and 50%. So we have used total pressure, total temperature as the inlet condition, and the velocity or flow is the normal to the boundary. Then the mesh connection at the diffuser mixing plane. Basically this mixing plane is very important in this study because the flow is coming out from the rotating component and going inside the diffuser, that is the stationary component. To match that flow, we have used a stage mixing plane average scheme which is available in CFD, CFX model. And what it is doing, whether it is from the rotating component, it is averaging the flow or flux on the one side of the that interface which is towards the rotating component, and that average flux flow is going inside the diffuser vane, or we can say stationary domain. The turbulence model is also one of the main concern. What are the turbulence model we can use our CFD prediction? So we have used basically two equation, base K omega and K epsilon model. So impeller is a different characteristic, having different character because of rotating component, and diffuser is a different characteristics because of a stationary domain. So two equation model like as SST or shear stress turbulence model or baseline turbulence model we have used to capture the boundary layer separation. And diffuser exit pressure we have used as the average static pressure. And our reference total pressure, total temperature like as a sea level only. So the first aim, like as I told, our first aim was to predict the performance or CFD modeling, whether it is our prediction is proper as per the test data or not. We have predicted our CFD model, and you can see the red color graph. In the graph, red color is the total pressure ratio, which is from the test rig, and our total pressure ratio from our CFD modeling is the you can see a black diamond. That is significantly matching with the test data, total pressure ratio. With this confidence, we went ahead and we predict our CFD performance curve, performance characteristics for the diffuser for the LSDV, basically impeller diffuser stage, which is baseline, then 50%, 75% and the 50%. Move to next. So this prediction is showing us, our CFD modeling is showing us that yes, the total pressure ratio for the 75% vane height is higher compared to the 100% vane height diffuser vane. So it means the pressure, the compressor, usually the aero designer looks towards the compressor if it is giving us higher pressure ratio with the low temperature, and based on that we will get the higher efficiency. So with same mass flow rate, if we will get a higher pressure ratio, that compressor is the acceptable as per the industry. It is also the compressor efficiency or compressor performance is also directly related to our specific fuel consumption. If our compressor efficiency is higher by 1%, it is proportionally relative basically. So if 1% is higher, then HFC is going to reduce by 1%. So the aero designers are mostly interested towards the high pressure ratio compressor, which will provide us high efficiency to get the reduced specific fuel consumption. So here you can see the total temperature ratio, and next is the efficiency. So you can see the efficiency for the 75% vane height is much higher compared to the our other baseline and 50%. How it can happen, that also we studied here. It might be a separation loss, it might be a pressure loss in the diffuser vane, it might be a shock loss. We have predicted that here. So you can also see the operating range, the stall point towards the left side is also that lower mass flow rate we have gained here with compared to the other baseline and 50% simulation. So here also you can see the diffuser loss. Basically it happened why we have received a higher efficiency in the 75%. We can say we are getting the lower loss in the 75% vein. Why? Because there is a separation that we have shown in next slide. So lower loss we have predicted for this 75%, and that's why it is showing us a higher efficiency. Now come to the some flow characteristic, flow field. So here we have predicted, we have took that max efficiency point in each case, like as baseline 50% and the 75%, and basically at a constant mass flow rate we have took one case, and we have introduced some span-wise calculation. Span-wise turbo surfaces means planes like as 10%, 50% and the 90%. 10% span is near to hub, 50% is mid of the span, and 90% near to shroud. So you can easily see the flow characteristics, that the total pressure ratio, total pressure basically in the 100% and the 75% speed, 75% vein height. So total pressure you can see the this left side at 10%, I think this is 10% span, and 50% span and the 90% span. So easily you can see it's a varying, and higher total pressure we are getting in the total pressure for the 75%. So here is the Mach number. Where we are getting a lower Mach number, it means there is a low velocity. Low velocity means there is a flow separation. So flow separation means we will get the separation loss. So separation zone in which cases is higher, that case is having low efficiency. So we have found at the 10%, 50%, 90% different span location, our 75% diffuser vein is providing the low separation zone. So it means our flow is more aligned or more streamlined with respect to the component compared to the others. So this is the another study which we have done by getting that confident in the 75% baseline and 50% prediction vein height. We have introduced some gap at diffuser hub at the diffuser shroud gap. So we got some result here. So this is the result for the hub gap, and this is total temperature ratio, and this is adiabatic. So here is the some conclusion that lower temperature, lower performance for vein diffuser we are getting, for diffuser vein height is changing, and both gap case are benefited towards the high operating range, but it is decreasing the performance. So that's all from my side. So I'm open for question.
Thank you, Sailesh. Thank you, Sailesh. Do we have any question? Anything? Okay, it was a quite interesting topic, and I thank Sailesh for the presentation and showing us the work that you have done and Honeywell team has done. We'd like to present you with a certificate, appreciating your work and the presentation. Certificate. Thanks, Sailesh. With this, we will move to the next talk for the track today. I would like to invite Mr. Kishora Shetty and Mr. Harsha Ramchandra Murthy from Boeing to talk about their work on additive manufacturing of threaded parts for the aerospace application.
Good afternoon all. Thanks for joining, and thanks to SAE for giving us this opportunity. And again, also we would like to thank Boeing for giving us this permission to present this paper. Myself and my co-author Harsha will be talking to you today on additive manufacturing of threaded parts for aerospace applications. The flow is like, we'll give a brief introduction about 3D printing, as you all know, and then we'll get into little details on materials and process selection, methodology of torque calculation. So Harsha will explain on why we went into calculating the torques, representative images of few threaded parts, and results and discussion and future scope, actually including the experimental validation and then conclusions. As you all know, 3D printing, or also called it additive manufacturing, it is building a part layer by layer, okay, either using a metallic material or a polymer material. Normally used for generating complex nest shape and parts, and especially prototype. Okay, we will talk about rapid prototyping. So 3D printing will be very handy when we want to quickly build something and visualize that. Okay, so it is not possible in conventional manufacturing methods. Advantages include fast realization, which I told, and reduced part cost, reduced manufacturing and installation time. So these are the few additional advantages in addition to the complex shape and size we can realize using 3D printing. Coming to AM threaded parts, okay, so like it is not new but not much explored, because threaded parts are most critical, and you know 3D printing still lacks in terms of material allowables. But we thought, why can't we explore this further? There are some research and development done, and there is a patent by Boeing on threaded parts, okay, for flight test equipment for a large polymer part. But we thought, why can't we explore further and see whether we can adopt this technology for making fasteners. So integrated threads can be printed along the part, because conventionally we make first fastener, then we go for thread rolling as a separate operation. Reduced part quantity, integrated mechanisms, including like sometimes we need a single use parts, then 3D printing becomes handy. Flight test parts, as I mentioned, and then dummy hardware for simulating production parts, okay, the prototyping or proof of concept, or MVP we call, minimum viable product. So that type of scenarios, 3D printing will be very handy. Internal grooves, sealing, customized thread geometry are other advantages of using AM. Okay, as I mentioned, so we need not to go for a secondary operation of thread rolling or machining. So we can at a time realize these things using 3D printing. These are some materials library we have at Boeing, and this is not an exhaustive materials library, so you can see process and concerned materials which we can print using these different additive manufacturing processes. Many materials and additive manufacturing processes are available for manufacturing threaded parts, okay, but only thing we need to mature this technology in terms of printing thread or manufacturing threads using AM, and then arriving the material allowables. And this table is, like you can see, if you go to stereolithography, you have both plastic materials, metallic materials, then plastic laser sintering, then direct metal laser sintering, and fused deposition modeling. So these are different or well established additive manufacturing techniques with concerned materials which we can adopt to print the threaded fasteners. Now I'll hand it over to Harsha to continue the proceedings.
Good afternoon, everybody. I'm Harsha, and thank you, Dr. Kishora, for taking us through the introduction. So, just to set the context here as to why we kind of stumbled upon this opportunity for exploration of torque calculations for AM parts, is that, as Dr. Kishora mentioned, that there was a patented part which was printed and also available to us, but I did not find any application of it on the flight test. And when I inquired about it with our airplane leads, they said that we cannot allow it to be fixed onto the aircraft for flight testing, because simply of the fact that we don't have a torque calculation available for it, or a preset torque value is not available for AM threads for now. So hence we cannot allow it, or rather justify it for fixing onto the airplane. So at that time, I realized that this is a crucial area which we have to focus on and build upon, as to for threaded parts of AM, we can establish torque values, like how for the conventional fasteners we have quite an exhaustive list of the torque calculations. So coming on to the methodology of torque calculations, As I mentioned, for the conventional fasteners, we have quite an exhaustive way of describing it. And we here at in this particular paper, what we have tried to do is use the same approach of calculating the torque calculations, the formula basically, but using the allowables available for AM. So, and some assumptions, because we don't have certain factors like thread coefficient and other things, we have tried to assume at present what is for the actual material. We have used the same in the calculation, but going forward with some experimental validation, we should be able to derive those coefficient factors as well. So, this is a very simple torque calculation methodology, very well established. Target input torque is what we want to apply on as a pre-torque load onto the clamp, or onto the fastener. And we have torque coefficient K and nominal bolt diameter dB and target preload. And this is basically done by having three different types of bolt body failure, that is tensile load, shear load, and internal thread shear load. So these are all from the ASME standard. It's a regular formula what we have used. I'll just not delve into it much. Say for example, the tensile load for the first condition is obtained by this formula. We get a certain load value, the pre-torque load value, and then for the shear load as well, and also for the internal shear load also we find out the three cases. The minimum of the three would be the worst case scenario, for which we will have to define or take that into consideration and finally use that for calculating the torque values. So coming on to a few advantages, as Dr. Kishora was mentioning, representative images here. Say we have two flanges which have to be fixed upon. As we see, we have to have a bolt coming from the rear and the nut from the front in this case. And for that we need a kind of space, what we call as option space provision, and that's from the rear side. But if at all we don't have much of an option there, if we can print a thread onto a part directly where fastening is required, then we will be able to avoid clearance which is required for the bolt insertion from the rear or whichever direction. So we can reduce the overall space provisions requirement, and also print it as an integral part. Coming on to the torque values, what we have calculated with the previous formula, we have tried to use the allowables for the various materials of AM, like 18Ni 300 for maraging steel, stainless steels, SI10mg, the most popular aluminium available now, and TI6AL4V again on the titanium side, ABS and Ultem. So we have calculated for various standard thread sizes, but we don't want to limit it to the same thing, same standard threads, because sometimes we may have to have oversized parts. Like the patent which we were discussing, it had not a regular thread, it was an oversized thread. So using the similar methodology, we'll be able to calculate the thread torque values for other thread sizes as well. So overall on the what we have found out was that we have found out the torque values for various thread sizes with the present methodology, and the torque values can be considered at present as a good base to start with. That is, at present we don't have anything, and so this acts as a base for further analysis and evaluation on validation. And the listed torque values have to be validated through physical experimentation, which is our future work, immediate future work. And we have also identified potential AM methods for various materials, like as Dr. Kishore was mentioning about the stereolithography, and we have to fine-tune the processes as well on the machine capability as to the thread printing. And the main challenge in the threaded parts is to have complex geometry of threads, because thread printing is not accurate from an AM machine. Currently, we are using post-processing techniques like thread rolling or thread cutting over a base thread which is already printed, and making it to a finer thread later. So, but we have to find out the ways in which we can print a thread directly as a use, directly to use condition, and that would help us eliminate some of the post-processing required. And coming on to the future scope, as I mentioned, experimental validation is very much necessary. But before that, what we want to do is we have had some work in other team going on with extended FEM. That's a new technique which is being developed for analysis of AM parts using FEM. And we want, they are primarily working on the composite technology now, but we want to rope them in onto evaluating the thread profiles as well as part of extended FEM. So that will give us more understanding of what we have at present and what actually we can get as a result of the FEM analysis before actually going for the printing of the actual part and physical validation. But post this, we definitely want to go for the physical validation, print the parts, and actually experimentally validate the torque values. And a few methods of validating the torque values are like the movement check and the loosening check, that initially the thread is tightened and slightly over tightened, and then loosening check when we want to loosen the torque, it has to match with the previous movement check where exactly it was coinciding. And then finally, once we mark these 2 points, then once we tighten it back, it has to coincide exactly for the same torque value. And all these checks, we will be monitoring the torque using a torque transducer or a torque tightening device, measuring device. So with these 3 checks, we will be able to validate all of the threads what we print in a physical environment. Yeah, with this, I would like to hand it over to Dr. Kishora for the conclusion part. Thank you.
Thank you, Harsha. So as we briefly touched upon, so AM threaded parts show good potential for future aerospace application. So we did a humble beginning, so we have to progress further. So that's the thought process, as Harsha mentioned. Materials processes are available. Up to some extent, we have allowables, but we have to derive further. Deformations are expected in manufacturing of AM threaded parts, and these have to be counted for. Okay, so this is like when we do the post processing, whether we have that shrinkage or exactly matching the thread profile, all those things, or we need to do an end thread rolling operation subsequent to the 3D printing. That's something we have to explore. So that's what we talked about: physical part validation, realization, and establishing empirical torque values. That's a key immediate step now next for us. And we also, as I mentioned, we printed an representative threaded parts using PLA material. It has come good. Okay, so we were a little apprehensive how exactly the thread printing will happen. Okay, because there will be the chances of overhangings, but luckily we could realize in this plastic or polymer 3D printing. So we expect to adopt similar technology or process to the material 3D printing, and hoping for the success. And our paper is published already last week from SAE publishing platform, Mobilus. So feel free to download that paper and go through in detail. And in case if you have any further doubts, we are available to take any questions now and later also. Thank you.
Thank you, Dr. Kishora and Mr. Harsha, for the nice presentation. Do we have a question?
Thank you. That was a wonderful presentation.
Thank you.
I have one question. This is regarding the certification part of it. So can you just show some light on the certification of these kind of threaded parts? Any work that has been done so far?